Okay. Recording started. So lecture 6, we are continuing with local online planning. This is part 2. Part 1 was just about like why are we doing what we're doing? What is this local planning about? What are we expecting to get? And in this part 2, we're finishing off the job. Because in part 1, we just talked about what happens with deterministic systems. And now let's do it for stochastic systems. So this is just like from last time. My iteration has this dual view. Either you use this a recursive call or you use this like this iteration that you're doing on value functions. And if you view it as a recursive call, then this is how the function looks like. The problem is that even though we want to get an algorithm whose runtime is independent of the number of states, this is not the case here because we have this very inconvenient sum. The last time we said that, okay, an interesting special case is maybe that of deterministic systems, where the sum can be optimized away because the next state is just a function of the current state in the action. And if you have a simulator, then the simulator should be able to give you this next state. And then reasoning is that, well, okay, stochastic systems may be not so different from deterministic systems. So what can you do? Well, one thing you can do is that you sample next states whenever you need them. And so whenever you're in this call and you're trying to calculate what this backup is, then you can just sum up next states within a set. And what is this set? Well, okay, let's say this is a function. You can implement this function in two very simple ways. This should be just like the set of representative next states that you could get from the simulator. So if you have a simulator that can give you random next states, then you can call this simulator m times and collect the results, and that's what this set is. And you could do this on the fly, like shown here, or you could do this together with memoization, where if you have already generated next states for some state action pair, then you're not generating the state action pairs the next time you're visiting state action pairs, but you're remembering, your code is remembering that, oh, we have already generated representative states or next states for the state action pair, so let's just recycle it. So this is shown in sort of like with a Python code where maybe there is this global under bar C, and we are checking if this key is in there, so it's a dictionary, and if yes, then just return that. And if not, then we just do whatever the other code does. And remember that we have already done the sampling and then return. And so there's a difference. And maybe this code is doing a little bit less work. And also the interpretation of this is simpler as a way of just imagining that you have this Bellman optimality operator, and in the Bellman optimality operator, this sampling happens for every state action pair once. And you can also imagine that you do this sampling ahead of time, like not on the fly, and you just save m next states for each state action pairs that you will or may not encounter during this recursive call of this function Q. And just do that up front and then save it. And so that allows you to see the whole procedure as just a, where is that? As just using this sampled version of the Bellman optimality operator. See, it's like for every state action pair, we take a bunch of random next states. And for those, we are just summing up the result of this maximum computation and take the average and then add the immediate rewards to that. So this is like the sampled version of the Bellman optimality operator. Okay. And so then you can imagine that if you have this sample version of the Bellman optimality operator, if this operator is in a way close to the true operator, so t hat is close to t, use 0 or something like that, then if you use this sampled version of the Bellman optimality operator in this recursive call h times, and you look at what happens at the result at this initial state s naught, where you want to calculate a good action, then you can just use the result of this calculation as if there was no difference to the sampled operator and the true operator. So you just take the greedy action and run with that. So important to emphasize that this is being done on the fly in this online planning loop. So if you recall, we had our planner that was interconnected with the MDP. So here's the planner in a closed loop. So every time a new state is generated in the MDP, the planner is called, this computation is done, it returns the action, which is fed back to the system, the MDP, and then the MDP makes a move to the next state, and then the process repeats. So we're generating a lot of random next states. Okay, so the whole computation is being done in a closed loop fashion. By the way, the control people like to call this, or this type of procedure is called model predictive control. When you're using a model in a closed loop fashion to plan what action to take, and you do this computation every time you need an action, this is called model predictive control. And it's one of the major techniques that is used for a lot of control applications. So it's something that comes up, in multiple communities, and usually in control, this planning step is implemented in some other ways because they're not really thinking about the stochastic systems, but maybe they have a deterministic system. So then it's like, oh, let's plan some trajectories and things like that. So, but the idea is the same, like you're planning in a closed loop fashion. Anyways, so back here, so this type of implementation allows this interpretation that t is approximated with this t hat operator, and then we're hoping that t hat is a good approximation to t, and therefore this computation is going to result in an action that makes sense. And to see whether that is happening or not, we have a bunch of basic results. So here's one of the results. Call is the second policy error bound because it's based on the first policy error bound, which is on the next slide. So this says that if pi is a memoryless policy, so recall that the memoryless policy is nothing but a function that maps every state to a distribution over the actions. Okay, so pi is a map from states to distributions, but it's kind of awkward to write then that you have pi of s, and what is the probability of taking a So there is this underlying distribution that you could write it like this, but this is pretty awkward. So we just like to write this way. And this is the notation that probability people would use for denoting stochastic kernels anyways, but it's the same thing. And so here the condition of the lemma says that pi is a memorialized policy that selects epsilon optimizing actions with probability at least 1 minus zeta in its state. So what does this mean? It means that pi is just a memorialized policy like this. I use this notation. And for every state, it holds that this policy is such that the probability that it selects an action whose action value is epsilon close to the optimal value of the state has a probability, so this is sum over A, of at least 1 minus zeta, right? So if you look at this formula, what does it say? It's like it says given a state, what is the total probability if I choose an action A from pi? What is the probability that this random action is going to have an optimal action value, which is epsilon close to the optimal value? So like it's a near optimal action. What's the probability that such an action is chosen? And we require that this should be large. Okay. So that's the condition. And then the result just says that. So now notice that if you're following this policy, then it's a random policy in every round. Whenever you encounter some state, you're going to sample some action, then this continues. So if the policy is not in a round, it's not selecting a good action, an action which would be this would have this epsilon optimizing property, then things might get derailed. But the chance of this is not too large. And altogether, like this can happen many times. There could be many mistakes. And like if you use the policy for a long time, surely if there is a chance that a mistake happens, like a non-epsilon optimal action is going to be chosen, surely in a long enough trajectory, this is going to happen. Infinitely long trajectory, it happens for sure. But the later it happens, the less impact it's going to have. So the discount factor is there to save us because actions chosen later have a smaller impact on the total value. And so altogether, if you add up all the mistakes and everything, and you look at how well this policy is going to do, then you will find that this policy is doing almost as well as the optimal policy up to this factor. So there are two quantities here. There is the epsilon from this epsilon optimizing, and there is the zeta, which is the probability of not even choosing an epsilon optimizing action. So if you're choosing an action which is not epsilon optimizing, it might have a bigger impact because this is multiplied with the infinity norm. This zeta is multiplied with the infinity norm of q star, which could be as large as 1 over 1 minus gamma, although if you're lucky, then this is not that big. But if zeta goes to 0, then this term can also be put under control, and the whole error can be controlled by controlling both epsilon and zeta. So nothing really bad happens if you, with some positive probability, but not a large positive probability, you're selecting actions which are not that great, even though like the policy continuously samples these actions, and then so eventually it will select bad actions, but still nothing really bad happens. So this is kind of nice. It's kind of a nice continuity property of policies, if you wish. If both epsilon and zeta are under control, then the policy is going to be near optimal. And so when we are going to think about this sample-based algorithm, then we're going to have two types of errors to care about. One is this value error, the epsilon, and one is this zeta, which is like that with some probability, we might be choosing actions which are like outrageously bad. And that might happen because these next states that are sampled from the simulator that are randomly chosen. So that is a chance that the next states are sort of not representative of reality. So the sample average is not actually close to the true average. This may happen. And if that happens, then you may end up choosing a bad action. But since this procedure resamples every time, like in this online loop fashion, like these errors are not going to be sticking with you forever, right? So if you never resample, then maybe you could be worried about that. Oh, okay, like, and this error could be detrimental. Although even in that case, and you should be thinking about it, like whether this resampling is really necessary or we could get away with not resampling but recycling all these sets CSA between different calls. Whether you should be able to do that, and then what would you need to change in the whole procedure if you have to change anything. So what's the impact of recycling the randomness to, like, for example, if the simulator was really expensive to use, then you probably want to recycle all the randomness because you don't want to call the simulator too often. And well, long story short, nothing really goes wrong. You have to mildly, but not a lot, increase M, which is how many next states you are generating. If you're not planning to redo the sampling all the time. And the reason for that is because of the effective horizon. Like nothing really matters beyond the effective horizon. So like you should be prepared for roughly h, which is like 1/1 minus gamma times recycling the randomness. And we'll talk about union bounds. This just increases the sample size by a log h factor in an additive fashion. So it's like not a big deal. It's a log h over epsilon squared. More samples are needed. So it's a mild dependence, and the number of states won't appear. All right. So how do we get this result? Well, you can get this result by first proving an even more elementary result. And in this more elementary result, it has two parts. So one part just says that if pi is an epsilon optimizing policy in the sense that the average optimal Q value under pi is epsilon close to the optimal value at every state, then pi itself is epsilon over 1 minus gamma suboptimal at most. And the other part of the results is that if pi is greedy with respect to Q, then pi is 2 epsilon optimizing. And to close everything up, so you might then suspect that this lemma, this policy error bound 2, if this goes back, so here you should just show that pi is epsilon plus 2 zeta Q star norm optimizing, and then you're done. You can just use part 1 of this other lemma. And this part 2 of this lemma just says it's useful for other purposes. Okay. Part 2 of this lemma just says that if pi is greedy with respect to a Q function, then pi is 2 epsilon optimizing, with epsilon being the distance of this action value function Q, or just Q function, to Q star. And because of this, by the first part, this is a near optimal policy up to this decrease, this sort of another continuity effect. So this kind of tells you that it's enough to approximate Q star well in L infinity norm, then you're going to do well. There is this blow up, this factor of 2 over 1 minus gamma, and you should be asking the question whenever you see things like this, whether a blow up like this is avoidable or not, or this is a weak result because maybe this constant could be reused, but apparently not. Like, you can come up with examples. And we had a previous result that was saying a similar thing for state value functions. If v is close to v star, then a policy that is greedy with respect to v is going to be near optimal to the degree that v was close to v star. And again, there was this blow-up factor, which was something like 2 gamma over 1 minus gamma. And so now I added an example to that lecture note where that result appeared that shows that that factor cannot be improved. I didn't add an example for this one. Maybe this is going to be an exercise or something. So you should think about it. You've been warned. Okay. So the next ingredient that we need for arguing about the correctness of this algorithm, meaning that if M gets large, this algorithm is doing the right thing. M was the number of next states that are sampled at each state action pair, is Hoeffding's inequality, which says that if you have random variables which live in a bounded domain, like the 0-1 interval, and these are identically distributed and independent of each other, then their sample average is going to be close to the true mean, up to an accuracy that depends inversely on the number of values that you're taking the average of. So that's like the 1 over m, and this is under the square root. And there is also a price to be paid if you want a higher confidence. So zeta here is the error probability. So as zeta goes to 0, log 1 over zeta, which appears here, blows up, but is a very, very mild dependence. And so when the zeta dependence shows like this, you have log of 1 over zeta under the square root. We say that this is a sub-Gaussian tail. And the reason for that is that for Gaussian distributions, this is the tail behavior that you expect to see. An elementary calculation shows that. And we shouldn't really be surprised to see like a Gaussians showing up, because we know from our probability courses probably that sample means have the central tendency. They're gonna be distributed asymptotically normally, like a Gaussian distribution with appropriate normalization around their mean under really mild conditions. And so this tends to be a Gaussian. And so Gaussian has tests like this, so that for bounded random variables, we also see this should be of no surprise. This inequality is also tight. The example of Bernoulli random variables with common parameter 0.5 is the case when this is unimprovable. If you have random variables with much, much smaller variance, so Bernoulli's 0.5 parameter Bernoulli's have the largest variance possible amongst all bounded random variables that live on a 0-1 interval. And so that is the case which makes this inequality tight, which kind of foreshadows that you could have refinements of this inequality that the inequality would exploit, that perhaps these random variables have much smaller variance. So for example, if you take a Bernoulli with a small parameter p, then the variance is of the Bernoulli is p times 1 minus p, right? So that's like this function. So this is p, and like here I'm showing the variance of the Bernoulli. So at 1/2, you got the maximum variance, which is like 1/4. And otherwise, the variance quickly decays. And at 0, you get 0 variance. At 1, p equals 1, you get 0 variance, right? In both cases. And so if the parameter is really close to 0 or 1, you expect that maybe you are able to improve upon this inequality quite a bit. And lo and behold, that's true. And we are going to discuss later inequalities which have this property. But if you are not making any further assumptions about the random variables, then this is time. Okay, so finally, okay, what is this whole argument? So that this procedure is correct. So as I already explained, the procedure can be seen as just like the first two lines on the top. Is this recursive call of applying this sampled Bellman operator to the identically 0 function and doing that h times in a recursive fashion, and then looking for the greedy action with respect to the action wave function that you get at the end. This is your action wave function. And so if we know that maybe this holds, then we would hope that the policy that we also read out is going to be good based on the previous lemmas. And this will hold with high probability as long as the sample averages are close to the true means. So here is the sample average for the next states. And the details are in the lecture notes. You can set up a recursion for this error, where the error at delta h, so h is this parameter of like how many times you have called a sampled Bellman optimality operator. And you can look at the difference between qh and q star. There's not, and then you can set up a recursion that looks like this, and you end up with two terms. There is a recursive term, and then there is another term where the second term depends on how well t hat is approximating t at the fixed point of t, q star. And q star is this fixed function, which is helpful because then this is just like a standard application of Hovding's inequality. So that's shown in the bottom. If t hat is applied at q star versus t is applied at q star, if you would plug in the definitions, you just see that this is just Hovding's inequality, right? And so Hovding's inequality would say in this case, so there is this gamma because there was this gamma before. In both operators, there is the reward, but the reward cancels. And then there is this gamma, which goes there. And then there are the quantities that we're averaging. So they look like this. Their range is 1/1 minus gamma. And so if in Hovding's inequality, we said that the range is just a 0, 1, but if you have some random variables and they have a different range or span, the length of the interval that these random variables living in, so that would multiply the error bound, right? So here we had the error bound, and naturally, if this leaves, this xi leave in some interval of some length, then the length of the interval would show up in the upper bound. It's just scaling, right? Because you can always reduce this case to this other case by shifting and scaling. And so we shouldn't be surprised by seeing this 1 over 1 minus gamma. This just comes from the fact that Q star, the norm of Q star, the Q star values lie in the range of 0 to 1 over 1 minus gamma. So here, okay, we are using this assumption that the rewards lie in the 0-1 interval. And if they lied in some other interval, you just modify the argument accordingly. And then there is the inverse dependence on an m, and then there is the log factor. Oh, sorry, I should have divided here by a zeta. Okay, so that's it. Oh, so why do we have
So
this SA? What?
I was just going to say, so the argument holds with probability 1 minus zeta.
What argument? The argument, yeah. Like, yeah. So this will hold with probability 1 minus zeta. This inequality holds with probability 1 minus zeta. This last one, for this we use Hovding's inequality, and we have to use it SA times because we are taking the maximum deviation over all possible state action pairs, and there are SA of those. So for each of them, that is the set of events when Hovding's inequality doesn't hold for each state action pair. So there is all possible events, the set of all the events, and then there is an error event for each little SA, and they are somewhere. Each of them is going to have a probability mass of zeta over SA. So this has a probability mass of zeta over SA. This has a probability mass of zeta over SA. Each of them have this probability mass because that's how we are choosing the parameters in Hovding's inequality. And there are at most SA of this. And so in the worst case, these are non-overlapping. So in the worst case, we need to sum up all the probability masses. So SA times zeta over SA, that's just zeta. So the event when any of the errors are happening, like for any of the state action pairs, something bad is going on with Hovding's inequality, the probability of this bad event is at most zeta. So therefore, with probability 1 minus zeta, the good thing happens. And so that's the result. This argument where you're arguing with individual bad events, and you say that, wow, the total probability of all the bad events is at most the sum of the individual probabilities of the bad events, that's called the union bound. So in the future, when I just say, oh, we apply union bound, this is what I mean. This becomes so routine that people just like routinely just say, let's apply union bound. The price that we pay is going to be this logarithmic price. It takes a while to wrap your head around this. I know that. So it's like, it's worthwhile to spend some time going through this argument on your own and thinking about the individual steps and writing everything out. Once you do it a couple of times, you will see that, like, okay, yeah, this is actually pretty simple. Okay, so this is okay. So we see that if m gets really large, and we make zeta small enough, then we will be able to keep everything under control. But m, according to this calculation, should be at least proportional to log s, right? Because there is this log s here. So this argument shows that, Well, as long as m is big compared to log s, we should be fine, which is a big advance compared to having, like previous arguments, in order to control the error of the policy or cost of calculating an action, had to scale at least linearly with the number of states. So now it has to scale with the log of the number of states in some polynomial way. So that's a much better dependence. So that's an exponential improvement. So sometimes you can do this by using sampling, an exponential improvement. It's really great. But still, the number of states is there. So what if the number of states is like really, really large? And even this logarithmic dependence, therefore, is undesirable. Can we do something about that? Or is this procedure inherently limited? The answer is no, the procedure is not limited. We just have to do the calculations in a more careful manner. The details are, again, in the lecture notes. But basically, we'll need to argue for all the states one by one that are encountered when this function q is called. And you do that in a careful manner. Then at the end of the day, this theorem comes out, which says that we can choose m, the number of next states in this procedure, in the following way. So if you're given a delta, which is your target suboptimality level, so you choose your m to be this quantity or something larger. There is no dependence on s of whatsoever here. So C delta is just like this inverse polynomial of the delta and polynomial of the horizon. So you could also write this as 18 over delta squared times h to the power of 6. And so you choose your m like this, and you run the procedure, and it's guaranteed that this is going to generate or induce a policy which is at least delta optimal, if not better. And this is independent of the number of states. So this is really great. Like we see that we can win this. But the only worrisome part of this, of course, is this exponential dependence on age. Age is this effective horizon. So that's quite problematic if this is a big number. If the effective horizon would be really small, you have, for example, a discount factor which is near 0. You're so lucky. You don't have to plan far ahead in time. Then this is great. But if that was also big, then okay, like we won one of the games but lost the other, right? So we see that it's like this. How is this game called when you're like press on something and something other thing comes up? Like you have to be quick in like typing these things. Anyways, that game, it's like that, right? Like we reduced the dependence on number of states, eliminated it, and now another bad dependence comes up, which is an exponential dependence on the planning horizon, which we didn't have before. We had a polynomial dependence on the planning horizon before with value and policy iteration, but we had a linear or reverse dependence, a polynomial dependence on the number of states. All right. So this is kind of the end, and I just wanted to discuss in connection to this Baemon's curse of dimensionality, which I'm sure that you have already heard about. We don't know actually whether he was the one who invented, well, he didn't invent this term, but he invented maybe curse of dimensionality. So one of the papers that is saying this very clearly is this paper by John Rast, the title of the paper is Using Randomization to Break the Curse of Dimensionality, and it's exactly talking about this curse of dimensionality that we are also talking about. And the way the paper phrases it is like this. There is an important practical limitation to one's ability to solve continuous MDP's arbitrary accuracy Bellman's curse of dimensionality. This is the well-known exponential rise in the time and space required to compute an approximate solution to an MDP problem as the dimension increases. So what they are talking about here is that the state is not even discrete, but it lives in a d-dimensional space, and then maybe you need to you need to do something about this. So notice that the previous algorithm, we were doing as if like the fact that the number of states is finite matters for the previous algorithm. Do you think it really does matter for the previous algorithm that the number of states is finite? Or would it work if you have a continuous state space like this? Okay, let's open some voting. Let's have some fun. Paul. Start Paul ask question. Okay. Sampling. I'll go just this cause works. Okay. Last theorem holds without change. Without essential change. Even state space is okay. Option 1, yes. Option 2, no. Okay, lunch. You see the poll? I'm polling everyone on this call. Please respond. So the last theorem we're talking about is this, which says that you run this algorithm with m set in this way, blah, 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 and you get all these nice things. Okay, 4 votes. I guess only I see the result of the poll for now. Come bring it in. We have 18 people, so we are at 7 votes. Yeah, maybe I should stop talking and you can think. I can tell you it's pretty even. So that cannot be true. I don't see who is voting what. I think maybe at the end I can see. I don't know. But I don't care actually about whether you're correctly answering or not. Because it's all a game. It's fine. We can always be wrong. That's fine. Wow, it's so even. Okay, 6 votes for and 6 votes against. Come on, someone decided. And then I end the poll. All right, okay. This is okay, good. Okay. So there are 8 for and 6 against. Does anyone who voted against want to speak up and tell us why you were voting against? You want someone, please? Some disbelievers.
I can say something.
Okay.
I think so because of the previous theorem, like the error control one, we said that there's like a log s dependence on the error.
Mm-hmm. You're talking
So
about here.
yeah,
But then we also said that maybe we can get rid of that. Uh-huh. So that's why you were
yeah,
suspecting that there is an S dependence. I see.
yeah,
Yeah, it's true. Like if we stop at that point, then you have every reason to believe that some S dependence will be there. But this theorem, there is no S dependence. It uses a different union bond, where it's based on the observation that this algorithm essentially builds a tree. In every lecture, we have to draw a few trees, right? There should be no lecture without trees. So there is a branching factor of A because there are A actions at S naught. And then if you pick any of the result, then there is another branching with a factor of M because there are M next states, right? And then this will go on for a while until we come to the end of the tree. And so this argument, it is based on that, well, if you remember, this is a depth first recursion. It's like goes down and then comes up, up, and then one layer up, and oops, sorry, and then goes down, blah, 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 and so forth. So it visits states in some order. The total number of states that it can ever visit is how many nodes you can have in this tree, right? Which is that like, so here are the states. So altogether, the branching factor of these two things is M times A. So the total number of nodes, therefore, is like this, because at the first level, there is only one state. The next level, there are M times A states, and so on and so forth, up to the very end. At the very end, there are M times A to the power of H minus 1 states. So that's at the very end. And the states are visited in some order. The number of actual states is random because a state may re-enter multiple times at multiple levels. But we can always just like take this ordering in which the states are visited, right? And so so this creates this this visit order, and then you do the analysis in this visit order. If you do the analysis in visit order, there are at most n states where we need representative samples. And so there are at most n different bad things that can happen to you. So the union bound has to be applied with n, or can be applied with n. And n here is independent of the total number of states in the MDP. It only depends on how big this tree is. And so no matter how big the MDP is, it could have a continuous state space. The theorem is still going to be true. When you write the proof, maybe you have to be a little bit more careful because some sums need to be replaced with integrals or whatnot, but otherwise the theorem holds. And so, yeah, people who are voting that the theorem goes through without any change, they are right. People are not right, but that's okay. But the point is that, okay, so here, Joan is talking about curves of dimension in connection to just the dimensionality of the state space. And so we see this very simple look-ahead tree building procedure, which is going to have a runtime and space requirement that is independent of it's independent of how many states you have. Like, it doesn't care about any of those things. It's only dependent on the effective horizon, 1/1 minus gamma, and the number of actions, and the required precision. And the required precision appears in a nice way. The number of actions appears in a nice way. The horizon doesn't appear in a nice way in a bound. So altogether, the bound is exponential, but it's exponential in the horizon. So if we keep the horizon fixed, then there is nothing that's exponential here. So for a fixed horizon, this is just a polynomial expression, right? So if age is 3, then whatever, like I had m, and that was a function, a nice function of m, a and age, and data, and a, this raised to the power of age, they're just like 3, right? It's like a cubic dependence of fixed horizon. This is a polynomial dependence. Nothing bad happens if your horizon is fixed, as long as you're good with polynomials. Which kind of also tells us that maybe we are not that good with polynomials. If the order of the polynomial would be 100, then maybe we wouldn't want to use that procedure. But okay, that's a different story. But maybe the most important point here is that this exponential rise in time and or space happens only if you both have a large planning horizon and a dimension, or a huge coordinated state space. If either of these two are small, you're good. Okay, so this is an important refinement of this view. So no curse of dimensionality happens if you don't need to plan ahead, far ahead. Because then you can just like build these lookout trees. And what does it mean for practice? So it kind of also means that if somehow your problem, like you should look at your problem, and then somehow if you're able to reduce, for example, the horizon, and people probably have heard about options and whatnot, which could be interpreted effectively as reducing the horizon. It's like these are, like macro actions or whatnot that took multiple time steps. So it's like if you have your original horizon is 100 steps, but now you have these macro actions, and every macro action takes 5 steps, then your horizon, if you only consider macro actions, is going to be 20, not 100. Which could be a huge reduction, right? And then this look-ahead planning kind of procedures are going to work much better. So that's that just follows from whatever calculations we are doing so far, right? Anyways, this will come up all the time. That planning problems are hard, tend to be hard, only if the state space coordinate and the effective horizon are both large. And by now, we shouldn't be surprised. If one of them is small, then those edge cases we know how to handle. Look-ahead planning handles the edge case when the effective horizon is small, and dynamic programming handles the edge case when the number of states is small. So then what remains to be seen is what we do when none of the two are small, both are large. We have to invent something else. And that's what we're going to do in the rest of the course. So some extra reading for some extra fun is this lectures by an economist. The title of the lecture is All Curse of Dimensionality, Various Die Sting. And there are really interesting phrases in this lecture, like Monte Carlo propaganda. So I strongly recommend that you read this lecture. And if you have any questions related to this, we should also be discussing. I agree with maybe 50% of this lecture, just telling you ahead of time. You just have to figure out which 50%. Yeah, it's a fun lecture. Okay. All right, so let's turn to the questions from Slack. So we got some good questions. So excellent. Do you want to ask your question?
Yeah, so when we sample a few states and like, okay, by sampling a few states, we didn't have to like worry about computation that would grow with the size of the state space, and only those few actions, only those few states would be considered in the computation. And my question was that, okay, can we do the same thing for actions? Now we have dependence on the size of actions. So if the size of actions is really large, then our complexity would grow up. Then like, what if we sample a few actions and do something with them, maybe to prevent this blow up with the size of the action space? I mean, like I was thinking that, for example, well, the problem would be here that we don't have an expected value that's like, and we can't really say that, okay, our sample mean is representative of the expected value, because now we have a max operator here over actions. And then I was thinking that maybe, well, for example, we can assume that the value is convex in the action. Like if you assume a continuous action space and then the value is convex over the actions, then you can maybe sample a few actions and then do a few optimization steps on that. But then I didn't know if this is like a reasonable assumption to make.
All right, so it seems that you almost answered your own question. You point out the difference, the essential difference correctly between dependence on states and dependence on actions. The type of calculation we have to do with respect to actions is selecting an action, which is good. It's a selection problem. It's a maximization problem because we have the rewards. And that's not the case for states. For states, it's just averaging. And then there, Monte Carlo propaganda comes in a way and tells us that you should just sample and you'll be fine, regardless of coordinates. And yeah, so the thing that comes to mind right away is, again, the most useful exercise of all that you were doing in homework 0, which is in needle in a haystack problem, right? Like that immediately shows that you can't really do anything about the actions unless you have some extra structure, right? Because if you somehow you invented some magical procedure, then like you would be able to find like that, yeah, using sampling or whatever, then you would be able to find a needle in a haystack faster than what the lower bound that you proved in homework 0 allows. So that's not possible. There's no magical procedure. Sampling, none of it helps, right? So that's why we were also looking at randomization or randomized algorithms in homework 0, because I knew that this question is going to come up. and no sampling can help you, can save you. So you need additional structure. So without structure, no. And we also had the lower bound that was for just planning that optima, right? Like if you have no restriction on the current of the state space, then no algorithm can do better than build this look-ahead tree, look at all the leaf nodes, find the needle, return the corresponding action at the root of the tree. So we had that lower bound already that showed an exponential dependence. It's like a to the exponential dependence on age, but the base is a. So if you want, you can put that into the exponent, that a, right? And you see that, okay, like a log dependence in the exponent on the number of actions, that's the best that you can have. You can't do better than that. So with structure, like convexity or concavity, so let's say action space is continuous and you have really nice concave functions, and all the Q functions that you would encounter, like Q star or whatnot, it's concave. Or maybe all the Q pi functions, I don't know, but then maybe they are all concave. Then that buys you the hope that maybe you can do something about this action path, like the complexity tends to blow up if you have large number of actions. Yes and no. I mean, concavity on its own doesn't necessarily buy you this, because it may be just too expensive to even point evaluate these functions, right? Like maybe Q star is too expensive to evaluate or estimate. It could be. So it's not taken for granted that this may help. It's actually not as well researched as it should be. So people haven't looked very carefully at this question. My gut reaction would be that this is a good idea, but you should also think about specific examples where these conditions hold. Actually, if you like operations research type of problems, this concavity property holds most of the problems that appear naturally there. In robotics and a lot of other examples, I don't think that any of this holds, and any of this is gonna help. So if you're happy with OR type of problems, and those are like gorgeous problems, then I think that that's a rich space to look at, and it may be possible that you can do much more than what we suspect that you can do with simple brains. But it needs to be done. It hasn't been done properly.
So if it's not concave, and let's say we do this like optimization anyway and just reach some local optimum, local maximum, that's still better than the where we started.
Yeah, I mean, like you can
It's
you can
like,
try to prove something like local improvement results, and a lot of people do that. It's okay. I'm less enthusiastic about those results. Those results are usually pretty easy to get by. It's just common sense, and I don't necessarily find them too insightful. So to me, it's more insightful to ask the question of whether some basic structure like concaveness, or you could also abstract this away. You could also say that, like, let's assume that there is an oracle that is able to maximize the reward function or the sum of the reward functions, or like some class of optimization oracles are available to you which can deliver good results under controlled conditions. And then you would ask like, oh, can I use an oracle like this? Because there is life beyond concavity. You don't actually need concave functions to efficiently optimize something, because you can have, I don't know, like other structure that helps you to optimize well. So yeah, anyhow, I think it becomes a question of taste as well. Like what you find interesting or useful. I find it interesting when there is a class of problems that other people care about, and then maybe there is a structure property for that class of problems that people haven't used to its advantage, to its greatest advantage yet, and you can find out whether it's possible to take advantage of this extra structure like concavity or not. And then that's like a crisp question. Whereas you say, oh, can I design an algorithm which improves upon some policy? Yes, you can. But is this like, it feels that it's not really giving us much guidance. But yeah, it's still a legit question. All right. Good.
Yeah, thanks.
Yeah, you're welcome. All right, Yulin.
Yeah, I was going to ask about how can we formally prove that M can be set independently from S, but now I think I guess I see the point. Is that maybe after the derivation we have gone through just now, we have achieved the lower bound that is independent from the size of the space, safe space.
Okay.
So yes, so maybe from this way we can come back and argue that yes, we can find the M that is independently from S.
Okay. Yeah. So yeah, like this that you underlined here, that statement was made at the beginning of the lecture notes, but at the end comes the result that says that, yeah, okay, you can actually do this. All right, good. So you were not missing anything except that like you just have to go to the end. All right. Humayun, am I saying your name correctly? Are you here? Maybe. Okay. I don't know. He's not here. Oh, you are here. Okay, you're trying to talk?
It has unmuted.
Okay. You unmuted yourself. That's good. No talk. Uh-oh. All right. I think that yeah. Okay. All right. So we go to the next question until you come back. So Alireza?
Yeah, hello. I think you basically answered my question in the first of the lecture. Yeah, just to like restate the question, what I was wondering about was that I expect this first lower bound that we proved in the lectures to be something that holds with some probability because there is a random element that is out of control of the agent, and there is always a chance that the planner gets like happen to get a, I think the name for that events was failure events, when the action when the next state that the planner gets from the simulator is noticeably different from the actual next state. And I'm wondering if that events happen too much to the planner, then the performance would be very bad. But I think the key answer was in that the first this is an expectation, like v pi is an expectation, and then the like the effective horizon and the lambda like damp the effect of that bad events. And yeah, now it's solved for me. Thank you.
Yeah, okay, great. I like it best when people answer their own questions. Yeah, I think that's perfect. It's not lambda though, but gamma. But yeah, good. So Humayun, have you?
Can you hear me now?
Yes.
Okay.
How do you say your name? First name?
The way you said it was correct. It's Humayun.
Humayun. Okay.
So for local planning, we use the sampling technique to get rid of the dependence on the state or the computational complexity. I was wondering, why can we not apply the same sampling technique to value iteration with tabular MDPs? In a way, could we not just look at a few entries in the table instead of all entries, and could that allow us to maybe drop a factor of S from the computational complexity?
Yeah, I'm not sure what you're proposing to do, because the way I see this planning algorithm that we were analyzing here is that it was just implementing value iteration in a recursive way, and it was just doing what you kind of like also saying that we should be doing, which is that instead of calculating the full sample mean, it uses samples to approximately calculate the mean. So what were you thinking beyond this?
So local planning only has to propose an action for the state that the agent is in.
Okay.
But value iteration computes optimal actions for all states.
Okay.
For example, so could the sampling technique be applied to all states at once, like the way value iteration does?
Right. So the only, like, the first thing that comes to mind is that wouldn't this cost us as much, at least, as the number of states just to write down the answer? Right?
That's
like
true.
for each state, if you want to record like what action to take, it's like it takes as much time as the number of states to just write down the answers. So which, okay, maybe there was an S to the power of, I don't know, 3 or something, and then maybe instead of, you would have just a linear dependence on S. So you could call the procedure that we have from every state. And as I was alluding to, you can write down the results, and that creates a policy, and you can just like use that policy, and that policy is like a randomly generated policy, which from any initial state, if you're setting M properly, is going to guarantee you a value that is data optimal, and it will have a reduced dependence on the number of states, but it will at least have a linear dependence on the number of states still. So is that what you were thinking?
That's helpful. But because I also saw a theorem that was saying, I think that value iteration cannot get better than S squared A. So,
I don't think that we had a lower bound like that. I think that we were talking about that it's really hard to prove lower bounds, which show that some polynomial dependence cannot be improved. I think that we had an algorithm independent lower bound though for S squared A for if you don't have a simulator, but you only have a table-based representation of the MDP, like these big tables for next state probabilities. For every state action pair, you have a vector, and then like you have SA of these of vectors of length S. And that's how the MDP is given to you. There is no simulator. We had a lower bound then that said that S squared A is the minimum number of computation that you have to do to write down a policy which is near optimal, completely write down the procedure. And that was based on the needle in a haystack argument. And so it goes back to the discussion we were having about in what way you have access to the MDP, right? If you have a simulator access, this lower bound doesn't apply. If you then the S squared dependence could be reduced to S. Okay, I think that I understood you. This is what you wanted to say.
Yes,
Like,
that was correct.
okay, so yes, so that
Good.
lower bound will not apply, but you will have another lower bound that is SA for the simulator access. If you need to write down, because for every state you have to write down what action you want to take, and then for even if your planning horizon is 1, that is, you don't have to plan ahead. You just plan for the immediate thing, the reward. You have a needle in a haystack problem with an array of size A, right? For every state. So that's SA. Yeah, okay. Great. I think we're done with the questions. And then there was another discussion I wanted to have, but we're 4 minutes late already. I think that we should still postpone. That will be the time when we'll have less things to discuss before, and then we can have this discussion about computation. But now we have 2 other things. Like I really recommend that you look up this extra reading. It's gonna be fun, and to discuss the points that this person's making. Okay. All right. So see you in 2 days, and good luck with submitting your solutions. Okay. See you.